This lesson deals with supplemental problem 10.4. You can find this problem in the ECE202 ebook in the Chapter 10 Supplemental Problem starting on page 7. Let's again take an example from ECE201. This is supplemental problem 7.6, which consisted of two resistors, an inductor, an independent current source, a voltage-controlled voltage source, and a single-pole, single-throw switch that's closed at t equals 0. Let's solve for V1 of t, but using the Laplace transforms. So we'll again use our 5-step algorithm. First one is to find the initial conditions of the reactive components. All right, that would be the inductor. But with this switch open, prior to t equals 0, there's no current flowing, so the initial condition would be 0. And that would just be a current source in parallel with this inductance, whose value is 0 divided by s, or just 0. Next step is to transform into the S domain. So our switch closes, and we connect up this part of the circuit. I get a 4 milliamp current source, which now becomes a step. Our voltage V1 of t becomes V1 in the S domain, and our other components just remain what they are. Next step is to perform an S-domain analysis. So I want to solve for V1. What I could do is sum the currents at this node. Think of this maybe as a reference node, because V1 is the thing I'm interested in solving for. So the current that enters is 4 milli over S. What's leaving is V1 divided by 2K, and then the current I sub L. What's the current I sub L? Well, it's going to be the voltage across this impedance divided by the impedance. So this node voltage would be V1, and this node voltage would be a minus 5V1. Take the difference of those two and then divide by the impedance, 12K plus S times L, which is 2 milli times S. We got V1 minus a minus 5V1, so that's 6V1. Multiply both sides of the equation by the denominator here. In other words, 2K times the quantity 2 milli S plus 12K. Multiply on this side of the equation, the 2K's cancel. I just get V1 times 2 milli times S plus 12K, and then this term 6V1 gets multiplied by 2K. 4 times 2 is 8, milli times K cancels, so I get 8 over S. Here I've got 12K, and here I've got 6 times 2, which is another 12K. So add those two together, get 24K. We now can solve for V1. So V1 is equal to this expression divided by this expression. So I've got 8 over S, 2 milli times S plus 12K, and then divided by 2 milli S plus 24K. Let's pull out the 2 milli from here and here, and they'll cancel. 12K divided by 2 milli would be 6, and then we have a K divided by a milli, so that would be 10 to the 6th. Likewise here, dividing this by 2 milli, I would have 24 divided by 2 is 12, and then K divided by milli would be 10 to the 6th. Okay, since the highest power of S is 1 in the numerator and 2 in the denominator, we have a proper rational function, and we can do a partial fraction expansion. So we could write this as some K1 over S plus some K2 over S plus 12 times 10 to the 6th. So we'll take this expression and multiply it by S, and then let S equal 0. Terms cancel, and so I get 8 times 6 times 10 to the 6th divided by 12 times 10 to the 6th. The 10 to the 6th cancels. The 6 and the 12 become a 2. And then 8 divided by 2 is 4. Likewise, to find K2, we'll multiply by S plus 12 times 10 to the 6th and let S equal minus 12 times 10 to the 6th. Cancel. And so we've got 8 times minus 12 times 10 to the 6th plus 6 times 10 to the 6th divided by minus 12 times 10 to the 6th. Okay, the 10 to the 6th cancel. I have minus 12 plus 6, which is minus 6 over minus 12. Minus signs cancel. 12 divided by 6 is 2, and then I've got that divided into 8, which is 4. So I could write V1 then as 4 over S plus 4 over S plus 12 times 10 to the 6th. And now we can find the inverse Laplace transform. Our step function, so it's going to have a strength of 4 times U of t. Constant 4 here. 1 over S plus alpha is e to the minus alpha t, so minus 12 times 10 to the 6th times t U of t. Again, let's write this as a time constant, so the reciprocal of this is equal to 83.3 nanoseconds, and so I can write my voltage V of t as 4 plus 4 times e to the minus t over tau, where tau is 83.3 nanoseconds, and all times U of t, and the units here are volts. And this is supplemental problem 10.4.